Okay, so let's get started with our lecture number 6. So last time we were discussing orthogonal basis, and today we are starting representations with orthogonal or orthonormal basis. So the difference between orthogonal and orthonormal is, so orthogonal basis means these vectors are pairwise orthogonal to each other. Orthonormal is they are orthogonal and normalized to unit norm. Okay. Of course, you are familiar with this orthogonality concept and orthonormal basis concept earlier on, but let's summarize it one more time. So this is our familiar space. So this is span of A1, A2, so the last vector is AK. So let's assume that all of them are independent. Then this is equal to, let's say, this set of vectors or this set of points in this span. So I have E1, E2, and the last one is E capital K. So the interesting thing is, these vectors are spanning the same space, so their linear combinations is always in this subspace. Okay, this linear combination or that linear combination. Well, the difference is, let's assume that EK basis is an orthonormal basis. Okay, so what's the meaning of this? That is EK transpose EL, this is an arbitrary K, one of these, and this another one, is equal to, so we are approaching single processing, delta K minus L. So what's the meaning of this? This is equal to 1 when K is equal to L. This is equal to 0 when K is not equal to L. Okay. So this is, you may say, our usual inner product between two inner product between two inner product of two vectors, not between. So there is angle between two vectors, but this is inner product of two vectors. Okay. So what is this notation? This is called Kronecker delta notation. Okay. So this is a definition in signal processing, as many of you know very well. If the argument of this Kronecker delta is equal to 0, I have 1. Otherwise, it's always equal to 0. So the argument is equal to 0 when K is equal to L, when these indexes are the same. So one of those numbers is K, the other one is L. That is it. Okay. So previously, we have seen that projection operation or mapping is independent of representation basis. So what's the meaning of this? So please remember, we have defined PA. So PA is equal to, I'm just writing it a little faster this time. It's a matrix like this. But what we have seen earlier, maybe I shouldn't write here A, but I should write range of A. Or the span of these, capital K vectors. So I would like to project over that range. So I can even write, if I wish, if there are two bases like that, I can write this one also as, in terms of E basis. I have something like this. So you may say, okay, if it is indeed the same matrix, what is the advantage of one basis over the other one, isn't it? So the issue is this one. Again, previously we have said that this is the Gram-in matrix. But let me remind you what E is over here. E is nothing but a matrix whose columns are these EK vectors. So obviously this is a n by k matrix, okay? So each one of these vectors is, let's say, n by 1. So this is an n-dimensional space, and this is a subset of an n-dimensional space. So that is it. Okay. So if I check this, E matrix is this, then, for example, the KL entry of this matrix, KL, is nothing but EK transpose EL. Because of this definition, EK transpose. So this is the KL entry of this matrix. Kth row, Lth column, entry. Okay? So I have this. So if they are indeed orthogonal, well, maybe you can also remember the following. This Gram-mean matrix is nothing but the matrix of inner products. So here is one of them. One of the elements of this matrix, KL entry, is this. And if they are indeed orthogonal, then I know that when the indexes are different, I get 0. So I get something like this. So what's the meaning of this? This E transpose E becomes, so this is a matrix. Entries of this matrix are equal to 0 when row index and the column index are different. Okay. And it is equal to 1, obviously, when I'm on the diagonal, when k is equal to L. Okay. So for example, 1, 1, entry of this matrix is equal to 1. Otherwise, it's all equal to 0. And we call this matrix, identity matrix. Okay. So this is a k by k identity matrix. So this is the advantage, you may say, the advantage of orthogonal basis. So this matrix becomes identity, and obviously then I end up with a simpler result, a projection result. Okay. Very good. Now, if I have an orthonormal basis, let's keep this drawing, then this B arbitrary vector map to this B star, then B star, this projection basis over, let me say A, but I think it's clear this is arbitrary. A is range space of A, times B. Okay, this is this projection point, which is, as we have discussed before, orthogonal to the span. Now, I would like to express this in terms of, let's say, let's do not repeat it one more time. So I get the following. So let me try to write this matrix. E1, E2, EK, and this is E1 transpose, this is E2 transpose, E capital K. So this is E transpose, and I have this B vector. So if I do this calculation, first row, first column, so I get this entry. So I get, at the end of this, I get this vector. First row, first column. Inner product of first basis vector and this arbitrary point B. Okay. Similarly, second row B. This goes like this. Kth row B. Okay. So this is nothing but the product of this matrix and a vector. It's a vector. So these are scalar entries. Okay. Then what do I get? If I multiply this one by this one right now, so this is just a scalar. So I get the following. Okay. E1 transpose B times E1 plus, okay, E2 transpose B times E2 and I have E capital K transpose B, I have EK capital K. because whatever this numerical value is, it's multiplying the first column, second numerical value multiplying the second column, and so on. So I can also write this as follows. K ranging from 1 to capital K. So I have EK, this vector, times EK transpose B. That is it. Okay. Now the projection result is very simply expressed. Now you can say that this is the expansion coefficient. Expansion coefficient of B star in this subspace, in let's say range of A. Okay, in that subspace. Because it's just a scalar multiplying this basis vector. Well, very good. I am sure you remember this, because this is something very basic, but maybe it's a little bit difficult to see because of our n-dimensional notation. So if I have, for example, a vector B over here, and if this is in a two-dimensional space, okay, a vector B. So I am projecting this vector B, it happens to be on the two-dimensional space, to the same space. So let me call this E1, let me call this E2. So this is their orthogonal and so on. Familiar, Euclidean geometry picture. So it happens that our given B is in the span. Okay. You may think about it like that. Or this basis vector, there are so many that it covers the whole space. Okay, subspace is equal to the space itself. Okay. Now how do you do this? Now you say that, okay, this is my vector B, and maybe you remember. So there is an angle of theta between this and this side of the triangle is magnitude of B cosine theta. This is purely geometric. I'm not introducing any inner products and so on. This is classical geometry. But now I know that, let's say this E1, E2, they are unit norm. In other words, they are orthonormal, as you see over here. So if that is the case, then this is equal to E1, because this is 1, B cosine theta, and this is nothing but inner product of E1 and B. So let me write inner product like this one. But I prefer linearity for the first variable, because I write it, this is constant in my opinion. This is like a variable. Okay. So I get this, well, distance is equal to this. So how about this vector? This vector this is unit norm vector. Now it is this vector. Now the value or the norm of this vector is BE1. And it is nothing but, it's in the same direction with E1. Okay? So let me write it a little better. I have this. Now I will repeat the same thing with this, but let me introduce another angle over here, let's say phi, do the same calculation. Then at the end you get this green vector. So the norm of this green vector is B vector, well, I think we can write a little faster, B, E2, and E2. Because this norm is nothing but, this coefficient is nothing but, norm of B, norm of E2, and angle between them. Okay? So this has unit norm, so this is equal to norm of B times angle is phi, so cosine of that angle is cosine phi, so I get this distance. Again, I am done. So we are very familiar with this one because this is our basic method for decomposing a vector, especially in physics problems and so on. You decompose a vector, this is your normal, let's say, vector, and so on. We are doing this all the time. But what is different is, we are using right now inner product idea, and we see that that idea easily generalizes to n dimensions. Okay. So again, this is the inner product. So this is EK, this is B, and EK. Okay, let me give some examples. So examples for orthonormal basis. Number 1. So let me write this. Okay, let me first define. So my E matrices, again E1, E2, up to EK. So number 1 is E matrices, let's say identity matrix. Okay. So your E1 is 1 and I have n zeros. So your E2 is 0, 1. So this is n by 1. So you have 1 and n minus 1 zeros. So you have only one non-zero entry and so on. So this is the second non-zero entry. So this is called canonical basis. Clearly we see that, so this goes for all n. Last one is 1. So on. This is called canonical basis, as I have said, and it's clear that these vectors are orthogonal. Because if you take the inner product, multiply this vector and this vector pointwise, well, this non-zero entry never coincides with a non-zero entry, so I'm always multiplying either 0 by 0 or 0 by a number, so I get 0. So norm of this individual vector is 1, norm of this individual vector is 1, so this is indeed orthogonal and normalized orthonormal basis. So let me have a second example. So let me say DFT basis. So let's select first k columns of n by n DFT matrix as, let's say, our E matrix. So is this E matrix orthonormal? So that is our question. So let me erase this because it's closer to here. So maybe I should, well, there is a minor detail over here, but let me put 1 over square root of times DFT matrix. I think it will be clear eventually. So DFT matrix times 1 over square root of n is equal to, let me write this like f because very ugly looking. DFT is, for other majors, discrete Fourier transform. So this is 1 over square root of n, and I have 1's over here, 1 over here, w square, w to the n minus 1. So this is the, let me have one more, w square, wn minus 1, w to the 4. So entries of this, so this is, let me say this is n by n. This is n square. So entries of this matrices of this matrix, let's say, this is F, is R W to the KL, and W is equal to E to the J 2 pi over N with a minus sign also. So I have 2 pi N KL, okay? So specifically for this matrix, so you may consider, for example, this is n is equal to 0, this is n is equal to 1, this is n is equal to n minus 1, this column. So this entry is k is equal to 0, k is equal to 1, and so on. For example, this is equal to k is equal to 2 row and n is equal to 2 column. So for this one, I have k is equal to 2, n is equal to 2. So this is the reason that I have 2 times 2 for w to the power 4. Okay? It's a very special matrix, and as you know, so this maps time domain input, let's say, in terms of n, x of n, to capital X of k. So now the question is, if I select, for example, first 3 rows of this, or first 5 rows of this, columns, first 5 columns, or first 7 columns of this, do I have an orthonormal basis? Okay. That is our question. Okay, so let me call, for example, this is as E1, this column as E1, E2, and let me call this is like En. Okay, now the question is, so question is Ek orthogonal to El? Okay, if they're orthogonal, I can normalize them, but then I will get orthonormal basis. But orthogonality is it the case or not over here? So how do you check this? Well, if you say Ek transpose El should be equal to 0, well, since this is complex valued, we have to do a manipulation, a further manipulation. So this is valid for real valued vectors. But this is complex valued, as you see. I have, so this, obviously for other students, j is square root of -1. So I have imaginary numbers over here. Okay. I should say complex numbers over here. So how about that case? Well, for this one, I should update my inner product definition by previously, as I have said, by Hermitians. Okay. So this is inner product definition for complex valued vectors. Okay. Now, how can is it equal to 0? So that's my question. So let me try to calculate this. So Ek Hermitian ELS, so kth column of this. So you see 1, I have k, 2k, n minus 1k. But, so this is transpose only. Hermitian means I'm also taking the conjugate. So once you take the conjugate, you have, because this w is, this is an exponential. If you take the conjugate of this, you get a plus over here. So I have something like that. Times, now EL, WL, W2L, Wn minus 1L. So let's make a sanity check. Well, let's say this one. So 2, 4, it goes like that. For this one, if it's again 2, because of this conjugate, it's right now -2, and so on. So I should calculate this. So how about this one then? Now, if I calculate this for, let's say, k prime, a dummy index, what do I get? I get this multiplied by that. W, so let me start from 0 to n minus 1. W k prime k times, there is a minus sign, let me write bigger. W minus k prime times W, well, this goes like this, but this is L K prime. Okay. Again, a sanity check. When K prime is equal to 0 in the summation, this becomes power 0 times power 0. So I multiply 1 by 1. When K index is equal to 1, so I get minus K and L. When K prime is equal to 1. So it seems okay. So what do I get over here? Okay. But let's also be careful. There is this 1 over square root of n factor over here. So since this is multiplying columns, I have 1 over n factor over there. Let's do not forget that. Okay, it's good that we have remembered actually. So let me put it over here. So what do I have? So let me use my usual notation, j 2 pi n. So this k prime is common, I guess. So this is k minus l. Okay. So this is w. So let's look at this term. W to the power k prime times k. Because of this minus, this cancels. I think it's okay. Okay. So how about this? Now, what do I see is, let me move this k minus l, k prime over here. Let me call this like r. So this is r to the power k prime. Okay. So I have a series like this, r to the power k prime, when k prime is equal to 0 up to n minus 1. Okay. So I'm talking about this summation. So what is this summation? This summation is nothing but geometric series, and it's a finite geometric series, so it has only n terms. So I know this result from my earlier knowledge. I won't be proving this. It's very easy actually to prove. So I get something like that. So if you check this, then what do I have? Well, so I get 1 over n times 1 minus, so r is this one, e to the j 2 pi. So n and this n cancels, k minus l, and k prime is equal to n over here. So I get this, divided by y minus 2 pi over k minus l. Okay. That is it. Well, the issue is the following. So I get when k is not equal to L. When k is not equal to L, so let's say that, first of all, these are all integers. K is an integer, L is an integer. As you see over here, k corresponds to this row index. Now over here, L corresponds to, maybe this is easier. K corresponds to index of first vector, L corresponds to index of second vector. So if they are different, this is also an integer. So and then this number is always equal to 1, because e to the j 2 pi integer is equal to 1. Okay? So I get 0 over here. So what happens when k is equal to L? It's a little difficult to see from here, because when k is equal to L, this becomes 0. E to the j, I have 0 again over here. How about this one? This becomes also, e to the 0. So I have 0 over 0. Okay? So this is right now uncertain because of that. I don't know the value of this. But when k is equal to L, well, it's very easy to see from this one. When k is equal to L, this is 0. So I have e to the 0 to the power k prime. E to the 0 is 1. So it's always 1. Okay? It's always 1. Or when k is equal to L, so these two vectors are the same. So I'm multiplying this number by its complex conjugate. So I get the magnitude of this number, magnitude square. So this number has unit magnitude. I get 1. Okay? So at the end, after this multiplication, I have summation of this n unit ones over here. So their sum is n. This 1 over n cancels. In it, I get this. Okay. So indeed, we see that indeed DFT basis is an orthonormal basis. So this is the reason that in Fourier transform and in DFT and in other transforms, we have very similar, kind of inverse and forward mappings. So what do I mean by this? If E times E transpose is equal to identity, then this is nothing but E inverse. Am I right? If they are n by n matrices right now. Okay. So if this is forward DFT, then it's transpose or its Hermitian, let me say, for complex valued. Its Hermitian becomes its inverse. This is the reason that forward and inverse transforms are very similar looking, and there is only a sign change in the exponent in the Fourier transforms, DFT, and so on, because of this orthonormality. Very good. Okay, so we have also covered this. Now, let me erase this part. So we have seen at least two orthonormal bases. We also erase this. Now, question. Given an arbitrary basis, how can I find an orthonormal basis spanning the same space? So as you see, if you have an orthonormal basis, it brings some advantages. So you can use the regular component by component decomposition to represent a vector. Okay? But in general, not all bases are orthonormal. So how can I find one? So the answer is, this is a very important question actually, and its answer should be learned by heart. This is called Gram-Schmidt operation. As you see, the same name, Gram. Let me check how Schmidt is written. Okay. So this is called Gram-Schmidt operation. Okay, it's very important for our purposes. And as I have said, Gram is also appearing over here. Gram has lots of contributions to least square kind of studies. Okay. We will explain those things a little bit later on. So let me erase this part. Also this part. So what is the problem? So given A1 up to A capital K, we need, let's say, E1, EK, such that EK, EL, let's do this for real, is equal to delta K minus L. Okay? So as I have said, in many of these discussions, we are introducing the concepts by real valued quantities. But if you want to think about complex valued quantities, in many cases, in almost all cases, if you represent this T by Hermitian, then you are done. Okay? That will be the only case. So let's focus on real valued case. So here's the procedure. I'll write the procedure, and then later on we will think about it. Step 1. So E1 is equal to A1 divided by A1 norm. Step number 2. Let's say an x vector. X vector is E2 minus I have something like that. And my E2 is x vector unit norm. So let me write step 3. So x vector is, sorry, this is a mistake. So I have A2, this is A3. Sorry, I made many mistakes over here. So this is A2, this is E1, this is E1. Okay. So this is A3, E1, E1 minus A3, E2, E2. Then E3 is x divided by x. So I'm defining this dummy x and doing such calculation. So the last step, step K, is x is equal to AK plus one of these vectors minus I think some of you at least, well, should guess what we are doing over here. But let me be careful. Let me check this because I made many mistakes while writing. This is okay. That is it. So this is a k-step procedure. So first step is very easy. Now I have, let me use black one. I have A1 over here. This is a given vector. I am generating E1 by just making it unit norm. So this is my E1. Okay. So how about the second one? Now I am given, let's say, another vector. So let me have with some angle A2 over here. Okay. I have something like that. Now I say that let me find, this is the same E1, projection of this A2 over this E1. So this is a one-dimensional subspace. You may consider it like that. So I'm projecting this A2 to this one-dimensional subspace. This is the expansion coefficient, and this is, the point after this projection operation. So how do we do this? Now you say that so I have this vector. It is equal to summation of this vector. So this is nothing but A2, E2 projection result times E2. So it is this one. Sorry, E1. So I'm projecting over. Let me write. Okay, I'll write better. So this is A2, E1, and E1. Okay. So black vector is first projected over along this line. Okay. So as we have done this, so this becomes that. So how about this one? So if I subtract from this A2 this vector, so I get obviously this vector as x. So this is my x vector. Because as you can see, A2 is nothing but this vector plus whatever remains over here. So whatever remains is x. Then I normalize x, so I get this. So one other way of seeing this. So can you show that this x is orthogonal to E1? Because that is the claim. Well, take an inner product. Calculate the inner product of x with E1. So inner product of x with E1. So I have inner product of A2 with E1 minus, this is a number, but E1, inner product with E1 is just 1, because E1 is unit norm. So I'm cancelling these two, and I am done. So let me also write that. So X inner product with E1, okay, is what? So this is equal to, according to this, A2 inner product with E1, okay? Because of the linearity of the, so I'm putting this X over here. So because of the linearity, I have A2 minus, now this is just constant, A2, E1, it goes out. Then I have E1 inner product E1, okay? Because this X is equal to this whole thing. So that whole thing, first I operate with this, minus, so E1 inner product with E1, this is just a constant, because of linearity it also goes out. Since this is unit norm, this is just 1, then I have 0 over here. So you see that this X vector is orthogonal to E1. So how about this? Now if you check, is this X vector is also orthogonal to E1? Let's give it the same, try. X inner product with E1. So I have A3 inner product with E1. E1 inner product with E1 is again 1. So again they cancel. I get 0 over here. So about this. Now I have this time E2 inner product with E1. But I know that E2 and E1, they're orthogonal. So inner product of E2 and E1 is equal to 0. So this cancels and this is also equal to 0. So that I see that this X is orthogonal to E1. Is X orthogonal to E2? You do the same thing. Inner product A2 comma E3 over here. So I have this A2 comma E3, E2 inner product E2 is equal to 1. They cancel this time. So E1 and E2, they are orthogonal, this is equal to 0. So I see that at the third step, after this normalization, I generate E3, and E3 is orthogonal to the previous ones. So this goes on, okay? And if you complete this case steps, and if these vectors are linearly independent, you get an orthonormal basis. Of course, this orthonormal basis, definitely it's not a unique basis. If you start from A1, this. If you start from this one and go back, you get another basis, and so on. There are, many different bases. Some of them have different advantages over the other one. So one last thing. Now, how about this? Can you see this? Now, note that AK, one of these vectors, is a linear combination of E1, E2, up to EK. So it's a K vector over here. Why? Well, it's obvious. Because to introduce, well, let me write it just for the sake of simplicity. EK, let me move this to A's because it's easier. So to introduce E1, I need A1. To introduce E2, I need A1 and A2 at second step. To introduce E3, obviously, I need 3 of them. So you see that the kth orthonormal basis vector is derived somehow from these K vectors. Okay. So what's that means? So if I write my famous A matrix, of course, vice versa. A1 is related with E1, so A2 is related with, E1 and E2, as you see over here, because this X is, in relation with this. So it's double. So they are, of course, related with that. So they are related in that sense. So how about this? If I have A matrix over here, and if I have E matrix like this, so would you agree that I have such an equality? Sorry. So I have 0 over here, and I have numbers. So non-zero numbers over here. Let me put entries like this. Okay, so this is non-zero. This part is non-zero. So this is a upper triangular matrix. Upper triangular matrix. So what's going on? Well, nothing new actually. So if, for example, if this number is 2, first column on the left side is first column, you know. So this first column is multiplying this matrix. So this is 2 times E1, the others are all 0. I think we have studied this many times before. Just focus on the first column. First column is, forget about the other columns then. This matrix times first column of this one. And we have seen that this is just a linear combination of weights for the columns. So this is 2 times E1 is equal to A1. Actually, we have something like that. If A1 norm is 1/2, let's say it's 1/2, then E1 is equal to 2A1. How about this? Let me have 5 and 6 over here. So you see that A2 is equal to 5 times E1, 6 times E2. Okay? I'm just making up these 5 and 6. There are some non-zero numbers over here. But I can find these numbers very easily. For example, this one is clearly 1 over norm of A1. The other ones, I have to do some calculation, but I can get values for that. So what is interesting is that, so this is famous, A is equal to Q times R. This is called QR decomposition of A matrix. So over here, Q is a orthonormal or orthogonal, doesn't matter scaling. And R is upper triangular matrix. So there are some linear algebra packages, let's say in MATLAB and so on. You can immediately calculate this QR decomposition by a single command. And as you see, Gram-Schmidt is nothing but QR decomposition actually. Okay. Of course, this is another way of checking whether these vectors are linearly independent or not. İyi akşamlar. So, what do I mean by linearly independent? At the end of these steps, let's say at the K step, if you get a perfect cancellation over here, so that means that perfect cancellation means I have a 0 over here. That means that AK is a linear combination of, so there is a mistake, it's good that we have catch this, K minus 1, because all previous. Okay. So last one is a linear combination of all previous vectors. Okay. Then because of that I get 0, then I clearly see that this kth vector is in the span of the previous vectors. So this is another way of checking, as you see, linear independence. If you get a 0 vector over here, clearly this new vector A2 is a linear combination of the other vectors, previous vectors that you have generated, E1s, E2s, and so on. Okay, so let me see what else can I say. So next time we will discuss positive definite matrices. It's an important topic. We will do a brief optimization study, and that will be completing our linear algebra review. Thank you very much. See you next time.